So, in order to talk about referential integrity constraints, we introduce the notion of a foreign key. A foreign key is something in a scheme which a group of attributes which would be used to refer to tuples in other relations, that is what we call a foreign key. And the referential integrity constraint basically says that this kind of referencing should be to existing tuples in the database instance, and there should not be any dangling references. Okay. So, if there are any questions in that, we can take it up. In this class, I am going to give you a set of an example database, an example relational database, and I am going to kind of continue using this example throughout this module and also in the SQL and other later modules. So, it is going to be important to clearly understand this relational database scheme, and we will keep it. I suggest that you write down this just the relation and names of the attributes separately in a sheet of paper, so that it is accessible to you when we are discussing queries and SQL and things like that. Okay. So, so let us go ahead with this. So, we have this database is to capture the academic details about a in institute which has a number of departments and students studying in the departments for various degrees. So, we have student relation which has these are the following attributes for the student relation. We have roll number, name, degree, year, sex, department number and advisor. Okay, so, here the convention in relational schemes, when you write down relational schemes, is to underline the key attribute. So, when an attribute or a group of attributes written together are underlined, what it means is that it is a key. Okay. So, roll number is obviously the key for this particular. So, if there are multiple keys, then there will be multiple groups of attributes which are underlined in the relational scheme. So, roll number is a key for this student relation, because the value of roll numbers can be used to uniquely identify a particular row or a particular tuple in the student relation, right. And so, name, these are obvious, degree is the program, the value of the degree attribute is the strings that stand for the various programs that the student might have been enrolled for. So, what are the degree for which he has joined the institute, and the year is the year of admission, and advisor attribute is the employee ID of a faculty member identified as the student's advisor. Okay. So, all students required to have an advisor. So, there is a advisor attribute for student which will take values that are from the employee ID, domain of employee ID of a faculty member. So, that way you will be able to identify as to who is the advisor for the student, and of course, if you want to know more details about the student's advisor, then you will have to look up the appropriate other relation. So, and here is the other relations, there are actually some more in the next slide. So, department is another relation, it has department ID, name, HOD and phone. So, phone is the department's office phone number. HOD is a faculty member who is the head of that particular department, who is kind of academically responsible for the running of the department, and what is the name of the department and what is an ID. So, we give some numbers for the department, so that they are easily identifiable and serve as a key. In this case, even the name could serve as a key, but we choose to have a department ID which is a number. Now, professor employee ID, because professors are all employees of the institute. So, there is an employee ID and name, sex, start year. So, start year is the year when the faculty member has kind of joined that particular department. So, all faculty members work in departments. So, what is the department in which a particular person is employed is given by the department number and then phone number of the particular professor. So, that these are the various attributes we have for professor relation. Okay. Now, next one is the other important things that we need to keep track of. Course. A course is a subject of study, right, and it has been named, it has been given a name, C name we call it, to just not confuse it with other names. So, C name is the course name and each course has certain credits, right, the number of credits that you earn if you complete that course, and then department number indicates the department that offers that particular course, and then the course ID. So, we use a course ID to kind of identify the courses. So, it will act like a key for the course relation. And then we have the issue of roll numbers, the issue of enrollments. So, students enroll for courses, Now, in this case we see that there is a need for taking a key which consists of 4 attributes. The reason being that course ID alone cannot be roll number and course IDs. A student typically does several courses in a particular semester, and so and a course gets offered multiple times across the years, right. Say for example, you are now doing CS 3700, the same course would have been offered last year and it will get offered next year and so on and so forth. And so, the year in which it is offered and the semester in which it is offered, that is the one that is in which a particular student is enrolling and obtaining a particular grade. So, because of this reason you need roll number, course ID, semester in which this course is running and the year, all of them to be part of the key for this relation. And what we will assume here is that this SEM attribute stands for semester and it has the value either odd or even, standing for the August semester and the January semester of the so we are in the odd semester now, though there is actually nothing odd about the semester anyway. So, the value grade, we will assume that the value grade will have null for the current semester and then will have appropriate values after the semester gets over. Okay. And so, for all the previous semesters there will be some value for the grade. So, that is how this is. Now, so you can see that the enrollment, the issue of how students enroll into courses and then obtain grades is all captured by this enrollment relation. Then we have from the faculty side we have we want to keep track of who teaches a course, So, we have a teaching relation which basically captures that a particular employee, a particular professor is teaching a particular course in a particular semester and a year. Okay. For example, so I am teaching this CS 3700 course of the odd semester of 2019 in the classroom CS 25, like that. So, that is one. So, naturally you can also see that the need for all of these attributes to be the key here, because no subset of this will be able to uniquely identify a row in this particular relation. an employee ID. Typically typically teaches several courses across the his employment, and so obviously that itself is not a key for this. And a course can be taught by several professors and also, so that itself cannot be the and then obviously you need to have this semester and year, only then you will see that a particular edition of the course is being talked about, and so you have the unique way I mean capturing that particular tuple. Okay. So, identifying the keys depends on the domain that we are modeling, and so in this case these are the keys. Now, finally, we also have prerequisite relation, which basically has two attributes called prereq course and course ID. And here, so if some tuple C1 C2 exists in this particular relation, what it basically indicates is that C1 is a prerequisite for C2. C1 should be successfully completed before enrolling for C2. So, that is the meaning of a prerequisite course. So, for example, data structures is the prerequisite for database systems course. So, you should have completed data structures before you take database systems course. So, there will be a tuple like that here. Okay. So, I hope the example relational scheme is kind of clear. So, we will use this relation scheme in this module and also in the SQL module. Now, I will show this entire relation scheme in one slide, so that we have it all one place, and now actually we will show what are the foreign keys here and where are they, what are they referring to. Okay, let us identify the referential integrity constraints and the foreign key, and then how what the foreign keys refer to. So, you can start identifying lots of these in each of these relations there are foreign keys. So, for example, here department number is a foreign key, right, because this is the one that we will use in the student tuples to kind of identify what is the department in which that particular student is available is present, and then we can use this to kind of link up with the appropriate department tuple. Okay. So, to refer to the computer science department tuple, so we will use the computer science department ID and then put it here, right. That is how we refer to the. So, to indicate this we have so those things will come up now. So, I will now indicate them by using these rows. So, for example, HOD is a foreign key in this department tuple department scheme, and it refers to the employee ID of the professor. So, one of the professors is the HOD, and so you have the employee ID of that particular person sitting here. So, and that can be used to refer to the actual professor who is the HOD for that particular department. So, you can see that this attribute has the the qualities that we are looking for a foreign key, which basically is a bunch of attributes that we use to refer to tuples in the other relation, and and the constraint here is that either it should be null or it should have values that are existing in the other column of the other referring the relation that we are referring to. So, likewise now we can identify. So, so prerequisite course and course ID are both foreign keys referring to the course ID, right. So, there are some more. Now, one thing that you will notice here is that the same attribute name might occur in multiple relations. Okay. And if there is an ambiguity as to which course ID attribute are we referring to, we will use the conventional dot notation to disambiguate that name. So, if you say course ID, then we are referring to this attribute. If you say employment course ID, then we are referring to this particular attribute, like that. And also the same kind of quantity is actually being referred to by two different names, like for example here department number and department ID. We know that they are in some sense the same kind of thing. So, but then we give the freedom saying that you can use whatever name you want, but then this is a foreign key that refers to that primary key of the other relation. Okay. So, yeah, so even in such situations it is not compulsory that this particular attribute name should be the same as this particular attribute name, that is what I am trying to emphasize. Okay. Now, let us identify some more of this. Employee ID obviously is a foreign key, refers to professors, and then roll number obviously is a foreign key in the enrollment relation, referring to student. So, even though these are part of some keys and all that, they can independently be foreign keys. Department number is a foreign key, refers to department ID. Then this department number here in the professor is also a foreign key, referring to department. Course ID here is a foreign key referring to that. Obviously here also course ID referred to, so this is also is a foreign key referring to that. And then here advisor is a foreign key that refers to the employment ID, and I suppose that is all. Okay. Department number here in the course refers to the department ID. Any more? Okay, that is it. Okay. So, this diagram is what we traditionally call as a relational schema diagram, in which we have the relation names, attribute names, keys which are underlined, and then we have arrows to indicate the foreign keys and what are the foreign keys referring to, what are the relations they are referring to. So, this particular slide I want you to note down in a separate page of your book, so that you can refer to this particular diagram when you are talking about queries in either relational algebra or SQL. Have it handy so that we can discuss this. Okay. Any questions about this? So, I think fairly clear. Okay. Now, let me start introducing the next major topic in this module, which is the topic of relational algebra. Now, we have seen the relational model, and relational algebra is part of this the whole relational approach to databases, and is basically a set of operators that take relation instances as arguments and return new relation instances, new relations. Okay. So, obviously it is an algebra, so it works on some domain of things. So, the things it works on are relations, that is why it is a relational algebra. So, it takes relations and produces new relations. So, each of the operators here are like that. So, we have a bunch of operators, both unary and binary, that take relation instances as arguments and return new relations. Now, what we will see here is that using these operators, we will be able to express the retrieval request. The retrieval, see, database has a lot of information, and we want to retrieve certain information from the database, right. So, how do you express your requirement? How do you express your query? It is called query in the database parlance, we call it a query. A query is basically a data retrieval request. I mean, we want this kind of data, this is what we want from the database to be retrieved. So, how do you express that? So, relational algebra operators give us one way of expressing what we want actually. So, but interestingly we can also see as we go along that this is a procedural way of expressing what we want, a procedural way of expressing what we want. That means, it kind of says that okay, you do this operation here on this relation, do another operation on the other relation, combine this like this and then combine it with something else and then give me this. Okay. So, when you have an algebraic expression, you can think of it as a tree, right, and so you can think of information flowing up like that, finally the output comes at the root in some sense. We will understand this as we go along and then discuss the queries. So, relational algebra forms the core component of the relational query engine. The relational query engine, which is the heart of the relational database system, uses these relational algebraic operators and efficient implementations of these operators. Right now, in this module we will not really bother ourselves with the implementation details about these algebra operators. We will think of them as logical operators and we will confine ourselves to the conceptual understanding of what these operators are. We will just think of them as mathematical operators and then see how we can make use of these operators. Later on, of course, we will need to study as to how to exactly implement these operators. How do you write a program to realize the operator? Okay, and those programs will go into the will all be available in the query engine. So, okay, so SQL queries. So, we will study SQL in detail, and SQL is a declarative way of specifying queries, a largely declarative way of specifying queries. We will see that later, and that is internally translated into relational algebraic expressions, as I was mentioning earlier also, and because of that it kind of provides us an opportunity for optimizing that relation, optimizing the way that particular query gets actually executed. Okay. So, we will see all this in this particular set of slides. So, what are the operators? It is surprising that we have just about half a dozen operators. Actually, you will see that the minimal set of operators is we will come to that a little later, but right now we just have 1, 2, 3, 4, 5, 6, 7, just about 6, 7 operators, and if you clearly understand these operators, this is kind of sufficient for expressing all kinds of queries on relational databases. So, that is the power of this particular the system, the algebra. So, we have select, project, which are unary operators, and a cross product operation, the union, intersection, difference, and you can also see that actually not all of them are really required. You can express some of them in terms of the other. So, let us say union, intersection and difference, and then join operator. We will later discuss as to what is the minimal set of operators and things like that. Okay. So, let us start looking at these operators one by one and understand the meaning of what those operators do. It is not necessary that you should be familiar with SQL at this stage of the course, but if you are familiar with SQL, do not confuse this select operator that we are going to talk about here with the select clause of SQL, and the select clause of SQL actually corresponds to the project operator. Okay. So, but even if you do not know SQL at this stage, it does not matter. Okay. So, let us start with the select operator. It is a unary operator, and basically it can be used to select those tuples in the relation instance that satisfy a particular given condition. Okay. So, it has a parameter which is the condition, and what it does is to select all those tuples in the relation instance which satisfy a certain condition, the given condition. And the notation here is to write it as sigma, theta and the relation operator, the input relation. So, theta is the selection condition, sigma is the select operator, and R is the relation name. So, it is a very simple operator. So, it basically takes a condition and then returns all the tuples in this relation instance R that satisfy that particular condition. So, it gives a new relation instance, and then it is easy to see that the scheme of the new relation instance is the same as the scheme of the input relation, right. So, result is a relation with the same scheme as R, the same set of attributes, same sequence of attributes, same order of attributes as R, consisting of those tuples in R that satisfy the condition theta. And the operation is commutative. So, if you write sigma C1 of sigma C2 of R, okay, notice that we can compose the operators and then get algebraic expressions, right. That is the whole idea of an algebra, right. So, you could sigma C2 R is now a new relation. So, I can now use that relation and then make another selection operation, right. So, sigma C1 is and then inside that I am giving this new this relation, which is the result of this particular doing selection with C2 on R. And you will notice that this is actually same as doing sigma C2 on sigma C1 R. So, if you are first selecting those tuples that satisfy C1, okay, and then from there you are selecting the tuples that satisfy C2, it is the same as doing first the tuples that satisfy C2 and then choose from among them. So, basically the tuples will satisfy both C1 and C2, and so the order does not really matter, and so this operation is actually commutative. So, it is this kind of identities involving this algebra operators that will later help us in rewriting these algebraic expressions, so that it will be advantageous for us to actually run the query in a efficient manner. Okay. So, that is the simplest operator, select. Here are some okay, let us go into the details about what exactly is the selection condition. So, a selection condition can be either a basic condition or a composite kind of condition. The basic condition will can be either of these two forms. So, you take a attribute and compare it with another attribute, or what are these attributes? Where are these attributes from? Obviously, they are from the relation scheme that is on which it is being applied, the relation on which it is being applied. So, these ai, aj are the attributes of the relation where that is the input for this operator, and so you compare those two attributes, some pair of attributes, or you compare an attribute with a constant, appropriate constant. Each of these attributes come from a certain domain, and so you have to, if you take a particular string, you cannot probably compare it with an integer, but you will compare it with strings, right. So appropriate things, appropriate constants, constants of appropriate type. So these are the kind of atomic kind of conditions, simplest of the conditions. The simplest of the conditions will involve comparing an attribute with another attribute and or comparing an attribute with a constant. So these are the simple conditions, and then you can combine these conditions with the logical operators. The logical operators are and, or, and not are all allowed, and then make a complex condition or composite condition. We call it, I am calling it as a composite condition. So basic conditions combined with logical operators, the and, these are familiar to us, we have been using them, so earlier courses also. So and, or, and not are to be used, and so all of them of course are Boolean value, right. So this is a comparison operator. Is A1 greater than A2, either it is true or false, right. So these are Booleans, so they can be combined with Boolean operators and or not, and then you can now get a composite condition, and that is how you will use that. So this theta is of this form. The theta, the selection condition is either a basic condition or a composite condition, and if it is composite, it is basically uses logical operators and then combines these atomic conditions. And what are the comparison operators? The comparison operators are the obvious ones. Here are the less than equal to, greater than equal to, and not equal to. The 6 possible comparison operators which compare values. Basically they compare values, and of course we will so in order for the we will assume that if you are applying this comparison operators, the corresponding domains are linearly ordered sets like that. The order relations do exist on those attributes, only then it will make sense for us. Okay. So C is a constant of appropriate data type. Okay. So let us start using this condition and then express a few data requests. So let us look at some example select questions. So obtain information about a professor with name Giridhar. Let's start with that. There may be several Giridhars in the institute. So now we are saying name is a attribute of professor relation. So this information is there in professor relation. The details of professor obviously are in the professor relation, and so what we are saying, and we want information that tuples that have Giridhar as the name. So we are putting a simple condition here, name should be equal to the string Giridhar in this relation professor, and then obtain all those tuples for me. So if there are multiple Giridhars, they will all be listed as. So the entire information about the professor tuples will be, so this now this is now stands for a relation, which has the same scheme as professor, okay, but contains only those tuples in which the name is exactly Giridhar, this string. Okay. So it is a subset of the original set of tuples. Now we have not yet given a name for that particular result, right. It can, we have to give a name in case we are using this this relation that has been produced by this particular expression later on in some other context, we may actually want to give a name for it. Okay. So we will see that later. So obtain information about professors who joined the university between 80 and 85, both inclusive, some numbers. Okay. So there is a start year attribute in the professor, which says that when the professor has started working in that particular institute or department to be specific. So here we are saying, so I use this short way of expressing and start year is either greater than or equal to 1980 or less and it is actually less than or equal to 1985 between exactly between these two things. So, this will contain the all the professor tuples whose start year lies exactly between 1980 and 85 inclusive. So, now these are typical data retrieval requests, and we can see that we can express them using this particular operator. So, moving on, let me also introduce project operator. The project operator, while the select operator was actually working on the tuples and then choosing a subset of these tuples, what the project operator will do is to help you to kind of get rid of unwanted columns in a relation. Supposing you want a relation is pretty wide and you want to focus on only particular attributes and you do not want to really look at all the attributes of the relation, then this project operator will be useful to you. Okay. So, what project operator does is to keep only the required attributes of a relation instance and throw away others in some sense. So, I do not want to other information, so I will just throw it away. So, okay. So, here is the notation. Pi is the symbol that we use for this operator pi, and here is a list of attributes that we want, So, obviously this and then this here is the relation on which we want to apply that. So, obviously each of these A1 through AK is part of the scheme of R. Okay. So, and they need not be consecutive or anything like that. So, some set of attributes from the original scheme which we are interested in. So, this list L is the desired attributes in the scheme R, and exactly what is the output or what is the result of this particular expression is given here. The result is the set of tuples V1 through Vk matching all this A1 through Ak such that Vi belongs to the domain of Ai, okay, for each of this case, and there is some tuple T in R, such that T dot A1 is equal to V1, T dot A2 is equal to V2 and T dot AK equal to Vk. Okay. There may be multiple tuples actually, but as long as there is some tuple in T such that this condition is satisfied, we take that bunch of values V1 through Vk and then put them in the output. Okay. So, basically remember that the result of a particular expression is a relation. So, and what is our definition of a relation? It is a set of tuples. Okay. And so, it will not have duplicates, it is a set. So, there is no scope for duplicate elements. Okay. So, that is why even if you there are multiple tuples that have these particular corresponding values V1 to Vk for these attributes A1 through Ak, only one subtuple of this V1 through Vk will exist in the relation. Okay, let me illustrate that. So, before we go further, so if R1 is the new relation name we are introducing and then assigning it as this one pi L R2, then basically we are calling this pi L R2 as this new relation R1, then the scheme of R1 is L, the projection list. What is the scheme of the output? The scheme of the output is this projection list, right, because that is what you are projecting. These are the attributes that you have chosen, the remaining attributes are all being thrown away. So, it is kind of obvious that the schema for the output is this projection list. So, here is the example, just look at this slide. Student, so we have Mahesh in computer science department, and there is a Mahesh in the mechanical engineering department, both of them are doing MS, etc. And so, now you do a sigma degree MS, degree equals MS on student and project name. Okay. So, now degree MS, so sigma degree MS on student will give me this tuple and the last tuple, the 3 tuples, because all of them are enrolled in the MS degree. Now, if you do a project name alone without projecting roll number, what does it mean is that I only need the column name or attribute name information of this particular relation and do not want anything else. So, now if you do that, then you will actually lose information, because only one Mahesh will exist and the other tuple contributes Rajesh, and that is it, you would have actually lost some information. So, you have to be careful about how to use it, but this just illustrates the idea that if you have a desired set of attributes and you project that, you get information corresponding to that. If you do roll number name from the student, supposing I just want to get only the names of the students, I am not really bothered about degree year and all this other details, then you would do pi roll number name on student, and then you will see that you will get, in fact you will get exactly the same number of tuples that are there in the student, because there are no there cannot be any duplicates in this particular combination of roll number and name, because roll number is actually a key. Since roll number is a key, you will get all these tuples. Okay. So, in this, basically in this lecture I have been able to introduce just these 2 operators, the selection operator and the project operator. We will just close with one particular point, that if R1 is pi L R2, then what about the number of tuples in R1? The number of tuples will depend whether the projection list contains the key or does not contain the key. If the projection list contains the key, then the output will be the same, the size of the output will be the same, exactly the same as the input, otherwise it can be less. I wanted to yes, in the previous example also it is clear. So, with this we will stop today. I will proceed with the rest of the operators in the next lecture. Okay.